Imagine pulling the engine out of a modern car and listing everything that is not inside a Ford Model T powerplant. There is no oil pump pressurizing the lubrication system because there is no pressurized lubrication system at all. The oil simply sits in a pan at the bottom of the engine and gets violently flung around by the spinning crankshaft, and whatever splashes onto a bearing surface is the entire lubrication strategy. There is no water pump circulating coolant through the block. The water moves because hot water rises and cold water sinks, and that basic principle of thermodynamics is the complete cooling mechanism. There is no fuel pump pushing gasoline from the tank to the carburetor. The fuel arrives because the tank is mounted higher than the engine and gravity does all the work. There is no distributor in any recognizable modern sense, no electric starter motor for most of the production run, and no fuel gauge of any kind. The engine and the transmission even share the same oil in the same casing, which means there is not a separate gearbox lubrication system to maintain or worry about. That shared oil arrangement deserves a pause because the Model T transmission is its own remarkable piece of engineering strangeness. It is not a conventional sliding gear gearbox with a clutch pedal. It is a planetary transmission offering 2 forward speeds and reverse, operated through 3 foot pedals and a hand lever that have no direct correspondence to anything in a modern vehicle. The left pedal selects low or high gear depending on how far you press it. The middle pedal engages reverse. The right pedal applies the brake. The throttle is a hand lever on the steering column. Learning to drive a Model T is not adapting your existing skills, but starting completely from scratch, which is exactly how owners describe the experience even today. This is legacy engines, and I spend way too much time thinking about why removing parts from a machine often makes it better rather than worse. If you're someone who is fascinated by the engineering decisions hiding inside the machines we take for granted, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Here is the thing most people get wrong about the Model T engine. They assume it was simple because the engineers of 1908 had not yet invented better alternative. That is not what happened. The engineers knew about oil pumps and water pumps and mechanical fuel delivery. They chose to leave them out. And understanding why they made those choices reveals a design philosophy that is more relevant today than most people would care to admit. So let us walk through the specification carefully because it is almost aggressively ordinary on the surface. 177 cubic inches of displacement, translating to roughly 2.9 liters. 4 cylinders in a straight line. A bore of 3 3/4 inches with a 4-inch stroke, making this a dramatically long stroke engine by any measure. Side valves positioned beside the cylinders down in the block rather than above the pistons in the head, giving you the classic flathead layout where the head itself is essentially a flat iron lid with combustion chambers hollowed into its underside and absolutely no moving parts. 20 horsepower at the crankshaft. 83 pound-feet of torque, which is surprisingly healthy for such a small displacement and comes directly from that long stroke geometry. A top speed of around 45 miles per hour under favorable conditions, and a compression ratio of just under 4:1. Now, you might be thinking that 4:1 sounds impossibly low, and you would be right to raise an eyebrow. A modern gasoline engine typically compresses its fuel-air mixture at somewhere between 10 and 12:1, with some high-performance designs pushing well beyond that. 4:1 means the mixture is barely being squeezed before the spark arrives, and that single number unlocks a tremendous amount of what follows, particularly when we get to the question of what fuels this engine could actually burn. But there is one genuinely advanced feature hiding in this otherwise primitive specification, and it is easy to miss when you are focused on all the missing components. The entire engine block was cast as a single piece of iron. All 4 cylinders, one monoblock casting, with a detachable cylinder head bolted on top. In 1908, that was genuinely unusual. Most contemporary engines were assembled from individually cast cylinders or pairs of cylinders bolted onto a separate crankcase, because pouring a complex 4-cylinder block in a single foundry operation carried a high failure rate and most manufacturers were not willing to absorb the waste. Ford solved the casting problem and committed to the monoblock anyway because a single piece is dramatically faster and cheaper to produce at volume once you have the process dialed in. And volume was the entire point of Ford's operation. So the engine is simultaneously primitive in its operating systems and genuinely modern in its manufacturing, and that paradox is the foundation of everything we are about to discuss. Think of it like a modern smartphone versus a basic calculator. The smartphone can do 1,000 things but has 1,000 ways to break. The calculator does one thing and will probably outlive you. The Model T engine is the calculator of internal combustion. It sacrifices performance, refinement, and convenience in exchange for something that mattered far more to its intended audience, which is the ability to keep running in places where no mechanic, no dealership, and no tow truck was coming to help. Every absence in this engine is a deliberate bet that reliability matters more than capability, and the production numbers suggest that bet paid off spectacularly well over the long term. And that is exactly where it gets really interesting. Let us start with lubrication because it is the system that most clearly illustrates the philosophy at work. A modern engine has an oil pump that draws oil from the sump, forces it through a filter, and delivers it under pressure through precisely drilled passages to every bearing surface in the engine. That system works extremely well and it requires a pump, a pickup tube, a filter housing, oil galleries drilled through both the block and the crankshaft, a pressure relief valve, and a warning light on the dashboard to tell you when something has gone wrong. The Model T has none of that infrastructure. Oil sits in the bottom of the engine, and the spinning crankshaft dips into it and throws it in every direction. Splash lubrication drenches the 3 main bearings, the camshaft, and the valve lifters in whatever happens to get flung at them during operation. It is unquestionably a worse system by any engineering metric you want to apply. Oil delivery is not guaranteed to any specific surface. It varies with engine speed and it is affected by whether the car is climbing or descending a hill, which changes where the oil pools inside the crankcase. And it is also completely adequate for an engine producing 20 horsepower at low revolutions with 3 generously clearanced main bearings and no particular ambition to operate at high speed. More importantly, it eliminates roughly half a dozen components that could fail and leave you stranded on a dirt road with no help coming. This is where it gets really interesting when you shift to cooling. There is no water pump anywhere in the system. Instead, the engine relies on Thermosiphon circulation, and the physics behind it is almost embarrassingly simple. Hot water is less dense than cold water, and therefore it rises. Cool water enters the bottom of the engine block from the base of the radiator. It absorbs heat from the cylinder walls. Having become hotter and lighter, it rises and flows out through the top of the block into the top of the radiator, where it gives up its heat to the passing air, becomes denser, sinks down through the radiator core, and returns to the bottom of the block to start the cycle again. The system circulates itself continuously with absolutely no moving parts whatsoever, powered entirely by the heat it is trying to remove. The hotter the engine gets, the harder the circulation works, which is a self-correcting arrangement of genuine elegance. It also explains why the Model T radiator sits so high above the engine. That is not a styling choice. The entire system only functions if the top of the radiator is above the top of the engine block, so that the cooled water has somewhere to fall back from under gravity. It is a beautiful piece of passive engineering, and it is also, if we are being completely honest, marginal. Thermosiphon circulation is slow. It depends on the engine actually being hot before it works effectively, which means the first few minutes of operation are the most thermally stressful. And it has very little reserve capacity when conditions get genuinely difficult. Model T drivers quickly learned to carry extra water, and boiling over on a long climb on a hot summer day was a routine part of the ownership experience rather than an emergency requiring immediate attention. Ford's own successor engine, the Model A introduced in 1927, added a water pump, which tells you that even Ford's engineers eventually concluded the Thermosiphon approach was a compromise they could no longer defend. Then there is fuel delivery, and this is where the story gets genuinely entertaining. No fuel pump exists anywhere on the car. The fuel tank sits under the front seat, which is above the level of the carburetor, so fuel flows downhill through a simple pipe. This works perfectly on flat ground, and it has one famous consequence that anybody who has actually owned one of these cars will tell you about with a mixture of amusement and genuine frustration. On a steep enough hill, the carburetor ends up physically higher than the fuel in the tank. The fuel stops flowing, and the engine dies. The solution, which became genuine folk knowledge across rural America, was to turn the car around and drive up steep hills in reverse. That is not a joke, and it is not an exaggeration. The Model T reverse gear was also low-geared, so the car had the torque to manage it, and reversing up the hill put the fuel tank above the carburetor again, restoring the gravity feed. Thousands of people did this routinely as a normal part of their daily driving. An engine so simple that the official workaround for its fuel delivery system is to point the car in the opposite direction. Look, I know what some of you are probably thinking right now. You are thinking that all of these absences sound like a recipe for disaster, not a blueprint for the most successful car in early automotive history. And you are not entirely wrong. Each of these systems is objectively inferior to its modern equivalent when measured in isolation. Splash lubrication delivers oil inconsistently. Thermosiphon cooling cannot handle sustained heavy load. Gravity fuel delivery fails on steep gradient. If you judge these systems by the standards of a modern engineering textbook, every single one of them would fail. But that is the wrong framework entirely. The correct question is not whether each system performs as well as the modern alternative. The correct question is whether each system performs well enough for the specific conditions this car was designed to operate in, while eliminating failure points that would leave a farmer stranded 40 miles from the nearest town with no telephone and no mechanic. And when you ask that question instead, the calculus shifts dramatically in Ford's favor. And that brings us to the one genuinely complicated system. The ignition on a Model T is the one area where the car is actually more complex than a modern vehicle rather than less, and it deserves careful attention because it contains both the most charming and the most dangerous aspects of the entire design. There is no battery and coil arrangement of the type that became standard in later decades. Instead, a Magneto built directly into the flywheel generates alternating current as the engine rotates. That current travels to a timer on the front of the engine which distributes it to one of 4 Trembler coils, one per cylinder, each of which steps up the voltage and fires its own individual spark plug. The 4 coils sit in a wooden box mounted on the firewall, and each one buzzes audibly when it fires. Model T owners learned to tune their cars partly by listening to the buzzing, because a coil that sounds wrong is a coil that is firing at the wrong moment, and the human ear is a perfectly adequate diagnostic instrument when the system is this exposed and this mechanical. There is a practical reason for this arrangement as well. Because the Magneto is driven by the flywheel, its electrical output depends directly on engine speed, and at hand cranking speed it does not always produce enough current to fire the plugs reliably. So a battery could be switched in for starting, and the Magneto took over once the engine was running and spinning fast enough to generate adequate current. 2 selectable ignition sources in a car from 1908, which is a level of redundancy that many modern vehicles still do not offer. But the ignition timing is where things get genuinely serious. The timing is set by the driver in real time. There is a lever on the steering column that physically rotates the timer, advancing or retarding the spark as conditions change. Not automatically, not through a centrifugal mechanism hidden inside the distributor, but by hand while driving, according to the driver's own judgment about engine load, road speed, and how the engine sounds at that particular moment. This is where the Model T stops being a simple machine and becomes a machine that demands to be understood. Because the spark advance lever is not a convenience feature or a performance tweak. It is a safety-critical control, and getting it wrong could literally break your arm. Before hand cranking a Model T, the driver must retard the spark fully. If the spark is advanced when you begin cranking, the engine can fire early during the cranking stroke while the piston is still traveling upward, and that combustion event will drive the crank handle violently backwards through the operator's hand and forearm. Picture the mechanics of that for a moment. You are standing in front of the car, bent over, with your hand wrapped around a heavy steel handle connected directly to the crankshaft. If the engine kicks back, that handle reverses direction instantly with the full force of a combustion event behind it. Broken forearms from crank kickback were common enough in this era to constitute a recognized category of medical injury, and the correct starting technique involved cupping the handle with your fingers rather than gripping it with your thumb wrapped around, so that a kickback would tear the handle out of your open hand rather than snapping your wrist. Retarding the spark before cranking was not a helpful suggestion from the owner's manual. It was the difference between starting your car and going to the hospital, and every single Model T owner knew it. So the Model T asks something of its driver that no modern car demands. Not skill in the sense of vehicle control, but genuine mechanical understanding. You had to know what the engine was doing at every moment and adjust it continuously, and you had to know why, because the consequences of not knowing were physical and immediate. Which brings us to the question of fuels and to a claim about this engine that needs to be handled with some care. The Model T is frequently described as an engine that would run on anything you poured into the tank. Gasoline, kerosene, ethanol, whatever happened to be available at the time. The accurate version of that claim is more nuanced than the popular telling suggests. The engine was designed and built as a gasoline engine, and it was not specifically engineered for multi-fuel operation from the factory. What is true is that its extraordinarily simple and robust design allowed a suitably adjusted engine to run successfully on alternative fuels, and that owners in rural areas did exactly that out of necessity. And the fundamental reason it could tolerate those fuels is that compression ratio of just under 4:1 that we discussed earlier. A high compression engine is extremely fussy about fuel quality because compressing a fuel-air mixture heats it, and if it gets hot enough to ignite spontaneously before the spark plug fires, the resulting detonation can destroy the engine from the inside out. Modern engines require specific fuels with carefully calibrated octane ratings precisely because their compression ratios are high, and putting the wrong fuel in a modern engine is an expensive mistake. An engine compressing at 4:1 is barely squeezing the mixture at all. It will tolerate almost any combustible liquid you pour into it, run badly on most of them, and keep right on going regardless. That capability mattered enormously in 1910, and it is easy to underestimate just how much. Rural America did not have petrol stations. The infrastructure we now take completely for granted, a filling station every few miles selling a standardized product, simply did not exist yet and would not for years. What farms did have was kerosene for lamps in large quantities, because that is what everybody used to light their homes. A car that would run, however roughly, on what was already sitting in the barn was a completely different proposition from a car that required a specific refined fuel you had to travel to town to purchase and hope was actually in stock. The multi-fuel capability faded over time for reasons of economics rather than engineering. Gasoline became cheap and widely distributed as the American oil industry expanded rapidly through the 19-teens and 20s, and Prohibition made ethanol production impractical in the United States for over a decade. So the flexibility simply stopped mattering to most owners, and the engine settled into its role as a gasoline burner for the remainder of its extraordinarily long production life. Now, let us talk about why all of this was done, because it was not an accident and it was not incompetence. Ford's primary objective was a car that ordinary working people could afford to purchase and, crucially, could keep running themselves without professional help. That second part is the one that consistently gets forgotten in popular accounts of the Model T story. In 1908, if you bought a car and something broke, there was frequently nobody within 50 miles who had the knowledge or the tools to fix it. There were no dealer networks, no service departments, no trained mechanics in most small towns, and no telephone in most farmhouses to call for assistance even if a mechanic existed somewhere in the county. Think about what a breakdown actually meant in that context. You are on a dirt road some considerable distance from anywhere, sitting next to a machine you do not fully understand, and there is no help coming. Whatever is wrong with the car, you fix it yourself or you walk home. So the car had to be reparable by its owner using ordinary hand tools with replacement parts ordered by mail from a Sears catalog and delivered by the Postal Service. Ford sold parts through the mail deliberately, and the Model T's entire design assumed that the person holding the wrench would be the person who owned the car. Every absence in the engine serves that goal directly. No oil pump is one fewer thing to fail and one fewer thing to understand. No water pump likewise. No fuel pump likewise. Splash lubrication cannot fail in any complicated way because there is nothing complicated inside it to fail. And when something did go wrong, the fault was usually visible to the naked eye. A car whose fuel system consists of a tank, a pipe, and gravity has a very short list of possible problems, and all of them can be diagnosed by looking at the components involved. Here is what most people don't realize about the production numbers that followed from this philosophy. By 1914, the Highland Park assembly process had been streamlined to the point where a complete Model T took roughly 93 minutes to build from start to finish, down from over 12.5 hours just a year earlier. That year, Ford produced more automobiles than every other manufacturer in the entire world combined. According to data from the Automotive Hall of Fame, by the time the 10 millionth car rolled off the line, 1 in 10 of all the automobiles on Earth was a Ford Model T. The engine, meanwhile, outlived the vehicle it was designed for by a remarkable margin. Model T car production ended in 1927 when Ford finally replaced it with the Model A. But the engine itself continued in production until 1941, another 14 years, because it had found extensive work elsewhere. Industrial applications, marine installations, military generators, and agricultural machinery all used the Model T engine because it was cheap, virtually indestructible, universally understood, and reparable by anybody with basic mechanical aptitude. When you have an engine that reliable and that widely distributed, you do not stop manufacturing it simply because the passenger car it originally came in has gone out of fashion. There is also an entire world of Model T modification and aftermarket development that grew up around the engine precisely because the base design was so simple and so plentiful. Aftermarket cylinder heads, overhead valve conversions, high compression heads, speed equipment of every conceivable kind. A significant portion of what eventually became American hot rodding culture started with people improving Model T engines because Model T engines were what everybody already had in their garage. The simplicity that made the engine easy to repair also made it easy to modify, and that combination created a grassroots performance culture that shaped American automotive enthusiasm for generations. So what is the honest final assessment of this engine? I want to be careful not to romanticize it beyond what the evidence supports. The Model T engine was not sophisticated by any meaningful standard, and by 1927 it was thoroughly outdated in almost every measurable respect. 20 horsepower was inadequate for the heavier cars and higher speeds that drivers increasingly expected. Thermosiphon cooling was marginal under sustained load. Splash lubrication limited how hard the engine could work before bearing wear became a serious concern. and the hand-operated spark advance was a genuine physical hazard that required constant attention from the driver. Ford's own replacement, the Model A engine, addressed most of those limitations directly, adding a water pump, a conventional ignition system, and roughly doubling the power output to 40 horsepower. But the Model T engine did the specific thing it was built to do more completely than almost any other product in the entire history of industrial manufacturing. It put people who had never owned a motorized vehicle into one, in places where there was no infrastructure whatsoever to support it, and it kept running because there was so little inside it that could stop. And it establishes a principle that keeps proving itself across completely different fields of engineering, from aerospace to software design to consumer electronics. Deleting a component is the single most effective reliability improvement available to any engineer because a part that does not exist cannot wear out, cannot leak, cannot seize, cannot be fitted incorrectly, and does not require scheduled servicing. Ford deleted the oil pump, the water pump, and the fuel pump, and sold 15 million cars. There is a hypothetical version of the Model T with pressure lubrication, a water pump, a mechanical fuel pump, and automatic ignition advance. It would have been a better engine in every measurable technical respect. It would have made more power, run cooler under load, lasted longer between overhauls, and been considerably more pleasant to drive on a daily basis. It would also have been more expensive to manufacture, harder to repair in the field, and would have introduced at least 4 additional failure modes that could leave a farmer stranded 40 miles from anywhere with no help coming and no telephone to call for a tow. Ford built the other version instead, and it is a significant part of the reason the 20th century looks the way it does. That is the trade that sits at the absolute center of this story, and it is not a trade that only applied in 1908. Every engineer designing anything makes some version of this same calculation. More capability or fewer failure points. Better peak performance or something a complete stranger can understand and fix with basic tools. There is no universally correct answer to that equation, and the reason the Model T engine is worth studying in such detail is that it represents one extreme of that spectrum taken about as far as it can possibly be taken and vindicated completely by the historical record. 2.9 liters, 20 horsepower, 4-to-1 compression, splash lubrication, convection cooling, and 3 pumps that were never fitted to any of the 15 million engines produced. 33 years of continuous production and an engine that could be understood completely by somebody who had never seen one before in their life. The Model T engine is not a relic to be pitied for its limitations. It is a masterclass in understanding the difference between what a machine needs to do and what it could theoretically accomplish instead. If you found this interesting, subscribe to Legacy Engines because there is a great deal more engineering history worth telling properly and in detail. And tell me in the comments, would you rather own a machine that is technologically sophisticated or one you can actually fix yourself when something goes wrong? And is there anything built today that would pass the Model T test of radical simplicity? I read every single comment. Thanks for watching, and I will see you in the next one.